Good afternoon, everyone. A warm welcome to all of you in the 8th talk of STEM's Qualifier Camp 2021. Today, we have Professor Manjunath Krishnapur with us. He is an assistant professor in the Department of Mathematics at IISc Bangalore. Let me give you a brief introduction about him. He completed his PhD from the prestigious University of California, Berkeley in 2006. He was a postdoc at University of North Carolina, Chapel Hill, and also at the University of Toronto, Canada. His interests are mainly in probability theory and statistics. Today, he will be delivering a talk showing how statistics is something which is inevitable in our everyday life, and we come across various results and polls and data every day, just like this COVID and COVID vaccination and everything. And also, he will show some beautiful and amazing results from statistics. Hope all of you enjoyed a beautiful tour of statistics. And over to you, Professor.
Thank you. Thank you. So I'm very happy to be here. And thank you for inviting me for this event. I'm sure you're all enjoying the lectures. So anyway, so as Mick already said, so I have this statistics for everyone. I hope the everyone part is true, and I will actually make it understandable. Okay, so because of internet things, let me just stop my video. I hope that's okay. Yeah, so let me now go to my presentation. Okay, why is this? How do I remove this? Okay. 1 second. There are various windows open. Okay. So this, I'm hoping to make it accessible, and please feel free to ask questions. I don't know what is your usual mode of asking questions, maybe on chat, or I'm happy to be interrupted. The organizers can interrupt me if there is something that I say which is not understandable. So the way I have done it is there are many pieces. So if you lose track of it, you can catch up again. Okay. So what is it? So in abstract, I said statistics everyone should know. Okay. So if you ask yourself, or sometimes we have to ask, so what mathematics should everyone know? Okay. Is there anything that everyone should really know? Let's say every educated person should know. Strictly speaking, not really much. Okay, so I may like my subject probability theory, but I think 90% of not 90, much more higher percentage of people don't know anything of it, and they are leading happy lives, and there's no need to interrupt it by introducing probability into it. So there are many specialized things in mathematics which all of us have, but they are not necessary to be common knowledge. What is necessary? So one of the basic things which is necessary is basic arithmetic. Everyone should know how to add and subtract and so on, because after all, you will buy and sell things in the market. You will buy vegetables, pay money, or you will invest in a bank, or you put money in a bank, or how much interest you get. These type of things are very basic stuff one should know. But in the modern world, I would say statistics also has become something that you cannot avoid. Every day you open newspapers, there will be results, polls, this, that. They'll say this percentage, last year it was like this, now this much. So everyone will be bombarding with numbers. So how to understand that? And so statistics is about making sense of these numbers and such things. Okay. So let me just proceed. So in the first two slides, I have some general nonsense about mathematics. So we can skip this actually. So mathematics, of course, is so it's the integral part of human culture. So what is mathematics is hard to define. So people say this is one of the definitions given. Actually, much of this is not necessary. So let me skip this. So in general, mathematics can be useful in other ways, not necessarily for the theorems that are there, but the concepts and languages can themselves be useful. And one of the nice features of mathematics, for those who don't know, is that it is the only part of human thought where we can make very long arguments which are actually reliable. Okay. So if you are discussing politics with me and I say something and you say, yeah, it's true, and I say something else and you say, yes, I agree. But after 10 such statements, you and I will be completely in disagreement, because all the yes is only approximate yes. So maybe you 90% agree with me on each statement, but if I make a series of statements, in the end, our conclusions will be completely different. So this is one of the unusual features of mathematics, that you can make very long serial arguments that you can actually rely upon. And the other useful thing about mathematics is you force yourself to make state the assumptions. Okay, even if you are not interested in mathematics per se, but in something about the real world, if it can be mathematically formulated, that means you will have to state the assumptions and stuff sometimes clearly, and that makes it sometimes for clearer thought. And there are other features like it is context free, which is actually a major source of frustration. People often ask when somebody talks about mathematics, what is this for? What is it about? It is not necessarily about anything. So anyway, so overall, mathematics appears to be useful for various reasons. So one of the things that I want to say here is one of the things that people say is mathematics is useful to uncover hidden patterns, but it's also useful to say that there are no hidden patterns, because that is a common fallacy people fall into. Okay. Anyway, so this is a little bit I had written about statistics that I already said in words like basic arithmetic and logical reasoning. This is today becoming important to know just to deal with the modern world. Okay, so now let me start my actual lecture. Okay, so every time a slide comes like this, so it is divided into several parts. I don't have to cover all of them actually. So I'm happy to be interrupted, but every time this comes, it means that you can catch up again. So if you lose track of what I'm saying, you can still catch up after when I come to a new topic. Okay, so it is divided into somewhat disjoint things. Okay, so let me say, so every day you see data and you make up your mind, you have opinions, etc. In newspaper you say something, you get angry, you get happy, various things, right? So let me give some data. Okay, so there is a dean of a college, maybe CMI or somewhere. Okay, so looks at some admissions data, and it turns out that 100 men have applied, out of which 57 were admitted, and 90 women applied, out of which 27 were admitted. Okay, so this type of thing we see all the time. Some data we'll see, and then immediately you will have some opinion, conclusion, whatever. So in this case, my question is, do you think there is possibly discrimination? Based on this, we can't say whether there is discrimination, but do you think that men are favored or not? So 57 men were accepted, but only 27 women were accepted. So does that mean that men are being discriminated for and women against? How do you interpret this? Obviously, I think everyone here will agree that just comparing, saying 57 is larger than 27, therefore maybe it is, that doesn't make sense. You have to see how many are applied also, right? So what you should compute is as a percentage. It doesn't make sense. If very few women had applied, there would be very few of them. So we should compute percentage, and we actually can easily calculate the percentage. So 57% of applicants were admitted among men, and 30% of applicants were accepted among women. Okay. So based on this, would you say there is, suppose you saw this in newspaper or somewhere, okay, would you say, would you feel that there may be discrimination, or maybe you don't feel it? So do you have an opinion? So is this a poll I gave you, Amit? I don't remember. Okay.
Yes, sir, there is a poll of yes and no.
Okay, so maybe you can just take a quick poll on this.
Okay, sure. So I'm
me-
just sharing a poll. People can select the option yes or no.
Yes or no? Yes means you believe there is somewhat of a discrimination. Maybe there are, we can't conclude what the reasons are. If you believe there is discrimination, or there is 27 percentage points difference between acceptance rate of men and women, or if you don't feel, if you feel that no, it is just is happening, I don't think there is any bias, then you can click that. So that is option 2. Option 1 is yes. Yes means there is discrimination. Okay. So I'll give you 20 seconds to poll. Okay. So
So I'm ending the poll now.
yeah, it's just progressing. Give it 5 seconds, and then
Yeah.
I think it has stabilized probably. Okay.
Yeah. Now I can end up poll.
So, okay, so it looks like, so everyone can probably see the results.
Yeah, so now everyone can see the result.
Now they can see. So 34 people have said yes. There is probably discrimination, maybe, but 28 people have said no. Okay, now unfortunately, I would love to, but I cannot ask you why you think this, why you think that, but make up your own mind. Let me proceed with the lecture. Okay, so based on this, what should we see? So the dean got worried. So he decided to look at a bit more carefully into the data. So there are two departments here. So he looked at department-wise data. So in department 1 and department 2, there are two departments in this college. So 90 men had applied to department 1, 10 of them to department 2. And with women, 10 applied to department 1 and 80 to department 2. And these are the admitted numbers. You see, 55 plus 2 is 57. 7 plus 20 is 27, right? So he looked at the percentage in both departments. What is the percentage of acceptance in department 1? It is 61% for men and 70% for women. In department 2, it is 20% for men and 25% for women. So do you see something a bit funny? In both departments, the acceptance rate is higher for women, 61 and 70 and 20 and 25. But overall, if you see, there is a stark difference of 27% in the other direction, 27% more acceptance rate for men as opposed to women. Okay, so what do you conclude? Okay, my business is not to give you conclusions. It is just to give you the moral that interpreting numbers is less trivial than you may think. So what is the so you have all this. So what of it? Well, how do you interpret it? Is there discrimination? Is there not? I cannot answer that question, and it's not my business too. All I am saying is that we see numbers and we interpret them, but as this example shows, interpretation of numbers could be quite tricky. It gives a completely different picture in the second one. That it's the same data, but when you see it department wise, it gives a completely different picture, right? So that's what I want to caution. So every day you see numbers and interpret them. So maybe do it with caution and some care. Okay, so what happened actually? So why did this happen? How is this? This looks a bit strange. So the thing is, what you see is that department 2 is somehow a very difficult department to get into. Percentage of acceptance is low for both men and women. Department 1 is something easy to get into, so higher percentage. But for whatever reason, more women are applying to department 2 and more men are applying to department 1. So overall, more men are getting admitted into the college. Although the percentage rates inside the departments are not really favoring them. So this is not real data, by the way, and the question is not also about discrimination, whether it exists or not. But real data do exist like this. So this is called Simpson's paradox. If anybody wants to read more into it, it's Simpson's paradox. You can read about it. This actually happens in real data. It's not an artificial phenomenon, although this data is just made up numbers. Okay. So let me give another one, a case of unhappy students, which is maybe everyone. Okay. So IISc, I am from Indian Institute of Science, Bangalore. So let us say IISc brochure, we have an undergraduate program. So they are always trying to attract undergrad students from places away from competing places like CMI or whatever, ISI and so on. So they want to do some propaganda for IISc. So our brochure may say, UG students, for UG students, it says, see, our IISc UG program is very attractive. Our classes are really small. On average, we have only 25 students per class, which is very obviously nice. It's a small number. Come here. But some students who have already been conned into joining, that is, who are already students in IISc, they violently disagree. No, don't believe they write on Quora or some online forum. No, don't believe all this propaganda by IISc. The average class size is more like 35. Okay, so you are some prospective student wanting to join or maybe not wanting to join. So how do you make sense of these numbers? So they are telling, so one of them must be lying, right? So IISc is lying or the students must be lying. How did this happen? So what I want to show, so this looks strange, right? I mean, they are telling completely different facts about this. Well, actually, it turns out strangely, maybe both of them are not lying. Okay, how do you decide? So here is a funny scenario. Imagine there are only two classes. Okay, there are only two classes. One class has 10 students, other class has 40 students. What will IISc say? Look, we have two classes. One class has 10 students, one class has 40 students. Average is 10 plus 40 by 2, 25. So that's what they have put in the brochure. But you look at it from the point of view of students. 40 students are in a class of 40, right? There's a class of 40 students. So 40 students say I'm in a class of 40. 10 students say I'm in a class of 10. So what is the average from the student point of view? If you ask student by student, what is your class size and add it up and average, 40 of them will say 40, 10 of them will say 10. And if you average that, you will get 34, which is close to what they are saying. So although they look completely contradictory information, both of this can be true. Again, what is the moral? Interpreting numbers can be tricky. So which number are you talking about when you say average class size? Which one is important to you? Is it this 25 or is it this 34? They're completely... So the point is, just because we use a word in English language or any language for that matter, like average, doesn't mean that has a real meaning. What is average? We use the word average many times, but does it have a meaning? Maybe not. Maybe, or it has different meanings. In this case, at least both of them can be called average from different points of view. Okay. So the point of this first one was this moral that you all the time interpret data, but be cautious. Interpreting numbers may require you to actually think. Okay. Now let me go on and introduce some very basic stuff in statistics, mean and standard deviation. Probably everyone has seen this. If not, it's the recap. In any case, this is just some basic facts about mean and standard deviation. These are two of the very basic quantities in statistics. So in later parts of the lecture, I may use them or I may refer to them. So I'm just putting it out here. Okay. So think of n numbers. Their mean is this x1. If you have n numbers, their mean is you just add them and divide by the number of them. So x1 plus up to xn divided by n. Standard deviation is a bit more strange object. What it is you take this mean, you subtract the mean from each of the original numbers, x1 minus mu, x2 minus mu, xn minus mu. You take them, you take the sum of squares, divide by n, and then take square root. It's a very strange thing to do. Why did somebody think of this crazy thing of doing something like this? Actually, what you should think of is, okay, you want to see how xi's deviate from the mean. So what one would want to do is x1 minus mu, x2 minus mu, xn minus mu, add them up and divide by n. If you do that, you will get 0. Okay. So because some of them are more than the mean, some of them are less than the mean, and they will always add up to 0. So that's why maybe it makes sense. I want to see how far from the mean in either direction it is. So I put absolute values and take the sum and divide by n. So this standard deviation should be thought of. I mean, this looks more natural. This quantity, this thing that I have written with absolute values looks more natural, but mathematically, this is a way more superior quantity. The sigma is a much more superior quantity. It goes all the way. I mean, for the simple basic reason. For that, okay, maybe I don't want to explain, but this goes all the way into mathematics. So if you go to higher levels of mathematics, people will say L2 space is but easier to work with than L1 space. The same point actually. Okay, so absolute values are a pain to deal with. Squares are much easier. That's why. But you should think of that as a superior substitute of this. So what it measures, that is the important. Both this quantity and the standard. This is called the mean absolute deviation. We rarely use it. The standard deviation is what we usually use. They both measure the spread of the data. If all the xi's were equal to the mean, then this would be 0. But if they are far away from the mean, but somehow some numbers are very small, some numbers are very large, and they average out to mu, then the standard deviation will be large. So it measures the spread. So this is something, if you have never seen statistics, you should just take this. I mean, this is a kind of a dogma that I'm passing on to you, but saying that in many situations, but not all. This is the cautionary warning. You can't apply it always, but one way of making sense of mean and standard deviation is the following, that 68% of the numbers are within one standard deviation of the mean. See, all the average is mu. How many are the numbers actually close to mu? Are some of them very small, some of them very large? What is happening? In many real life situations, 68% of the numbers are between mu minus sigma and mu plus sigma. That means they are within one standard deviation of the mean. 95% of the numbers x1, x2, xn are within two standard deviations of the mean. And 99% of the numbers are within three standard deviations of the mean. So this is true in many situations, not always, but it is true so many times that it is a useful thing. And where this comes from is this strange curve, which is this function e power minus x squared by 2 over square root 2 pi. If you have not seen it before, it is called the bell curve or the Gaussian distribution. So basically what I have drawn here is the curve, which is e power minus x squared by square root 2 pi. The area under that curve is actually 1. Okay, and here what I have shaded in the first picture, the shaded picture is the shaded part is the part of those part, the mean is in the center, okay, where this mode is, the mean is in the center, and this shaded part is the numbers which are more than one standard deviation away from the mean. So the shaded region in the first part is 68% of the area. In the second part, it is two standard deviations from the mean, and the shaded part is is actually 5%. Here it is 1%. So for many practical purposes, you can say 1% is, most numbers are within three standard deviations. Okay. So it doesn't mean nobody is above the three standard deviation. For other purposes, you may be actually interested in them. For example, if you are selecting students to CMI, which is a very selective place, you are not interested in people in the middle, but you are interested in people in the extreme. Hopefully not this extreme, but the other extreme. Okay. So that is what you may be interested. I mean, you may be interested in the extreme or you may be interested in the center, either, depending on the situation. So this happens. So many times this is true, but not always. When is this true? This is true. Okay, I thought I had written something more here. Okay, something is a bit strange. Hold on, give me a moment. Where did it? I had written some date. Okay, maybe I missed it. Okay. So what actually, when is it satisfied? So this type of thing is true for many measurements in real life. For example, if you take heights of people in a population, that will, so this x1, x2, xn are the heights of people in a, let's say, some small community or one city or one village or something. So they will satisfy this property, that this law. This is, you may say, this is a law of nature, that this happens, and this holds for heights of people. It also holds for some other things, exam scores, for example. So if you look at IQ tests and IQ scores, for example, they will satisfy this type of law. 99% of the people are within mu minus 3 sigma and mu plus 3 sigma, etc. So this is something that you should remember. This is actually one of the basic laws of statistics. In probability and statistics, we call it, you can call it central limit theorem or whatever. It is the appearance of the what is called the normal distribution, which is this curve, the Gaussian distribution. Okay, so this fact is a true one for many situations. And I have written here, the standard deviation is when statistics starts, and calculations with mean are more about averages. Okay. So why do you care about standard deviation? Just to give very basic. So you may think that the mean is important, right? But maybe standard deviation is important. Okay, I forgot to make a poll for this, but it's all right. So anyway, no need to make a poll. You can decide in your mind. So for example, let me give you two situations. Okay. So first situation is, I'm going to toss a coin. If it falls heads, I'll give you 200 rupees. But if it falls tails, you should give me 100 rupees. Okay. This is the deal. Or you can take deal 2, which is I'll just give you 25 rupees. Okay. So these are two deals I'm giving you. In the second deal, we don't do anything. No need to toss a coin. I'll just give you 25 rupees. In the first deal, we toss a coin. If it falls heads, I'll give you 200 rupees. If it falls tails, you give me 100 rupees. So unfortunately, I forgot to ask to make a poll for this, but it's okay. you can think in your mind which situation will you prefer. Okay, I have not. Luckily, I'm safely far away from you. I'm not actually offering you money, but let's make a mental experiment that I'm offering you all this. So, what will you? Which one will you? Which deal will you take? First deal or the second deal? Okay, so take a moment to think which one you would take. So, in most people would take the second deal. Although, if you see from the point of view of average, what is the meaning of average? You can think of an average gain. Here, in the second one, you will get 25 rupees. That is your gain. Expected gain is 25 rupees. In the first one, you will gain 200 rupees with probability half, but you will lose 100 rupees with probability half. So what is your gain? It is 200 into half minus 100 into half, which is actually 50. Okay, so in the first one, your expected gain is 50. So it's higher, but most people will choose this. And why do they choose that? Because this does not involve risk. So what is the difference between the two? The mean is higher in the first, but why are people choosing the second? Because no risk. In other words, no standard deviation. The less the standard deviation, sometimes you prefer, you're not always trying to maximize the average. Okay, that is the point that I'm trying to illustrate with this. Sometimes you are trying to minimize the standard deviation. For example, another example where you suppose you are traveling to your school every day, let us say school office every day. Okay, so you have many different possibilities. Maybe you can go by bus, you can go by metro, you can do something, you can take an auto to go some distance and then do something else, take another bus, etc. There may be many options. What will you do? You will choose, since you have to go every day, you will probably choose the one that will minimize the average time. Okay, so that makes sense in a way, to minimize the average time of travel, because you don't want to spend time traveling. But think of you are going to an airport to catch a plane. Okay, so there are two possibilities. There is a bus which takes 1.5 hours, or there is a train, because of various stops, it takes 2.5 hours. Okay, which one would you prefer? I will say that in most people would prefer the train, because bus is on the road and traffic means usually standard deviations are higher. So on average, it may be 1.5 hours, but sometimes it may be 1 hour, sometimes it may be 3 hours, etc. That's not good. If you miss the plane, you are gone. So, I mean, you don't get another plane immediately. So, in such a situation, you would rather go early and spend the fixed amount of time, even if it's larger, 2.5 hours, you would spend on the train. So there again, you are decreasing the standard deviation. In other words, you are being averse to risk, taking risk. That is decreasing standard deviation. Okay. Okay. So here is the single most important point in all of statistics and probability. This is the one point. If you don't get anything else out of this talk, so this is the most important law of statistics. I told you one before here, which may or may not have made full sense. Here is another one which may or may not make full sense. So you toss a coin n times, okay? How many heads do you get? Okay, if it's a fair coin, a usual coin, you expect half of them to be heads, but if I toss it 1,000 times, it won't be exactly 500. How many will it be? Can it be 400? Can it be 450? Can it be 300? The most basic factor in all of statistics is this, that you will get half n, but not exactly half n. It will be half n plus or minus a few multiples of square root 10. How many multiples of square root 10? That is actually defined by this law. With 99% confidence, you can say that you will be within 3 square root, so 3 square root of n, let's say, roughly speaking, okay? There's slight mistake there, but I will just stick to the mistake, it's okay. So let me say that you can say that you will get the number of heads in n tosses.
It's 3 o'clock.
Will be n by 2 plus or minus something like 2 or 3 times square root of n. That is how it will be. So if you toss a coin 1,000 times, you expect 500 heads, but not exactly 500. You will have a deviation from it of the order of square root of 1,000, which is maybe 30. Okay, so you will deviate from 500 by plus minus 30 or 60 or so. That's all. You won't deviate. It won't be as small as 400. So this is called the square root law, and it's the most important point in all of statistics. and the square root 10 is the standard deviation. Okay, the square root 10 is the standard deviation. So standard deviation is the one of the most important concepts of statistics. Surprisingly, it is not that old. It is less than 200 years old, maybe. Before that, nobody calculated standard deviation. So for something such a basic, one of the most basic quantities we calculate, it is really different. So what is the aspect of the square root 10 behavior of the standard deviation means here are two graphs. This blue graph is square root of x and the red one is linear growth x. So this standard deviation increases with n but not linearly but like the square root. That is one of the most important points in statistics. Okay, so depending on n, context n could be time, number of samples, etc. So actually standard, I can tell you another context where standard deviation is kind of very useful. Completely, I mean, so how does standard deviation occur? So suppose you have something like, so all my examples will be made up examples here, okay? So let us say two languages are there, Kannada and Telugu or something like that, okay? So which one came from which? So there are two languages in some adjacent geographical areas. So which one is came from which? So of course people love to quarrel in our country based on these questions. So it is good to know how to answer such questions. So did this language come from that one or that from this one? How would you figure out? The idea is like this. So standard, so you may not know backwards in time when something happened. So how will you do it based on the current one? So standard deviation is actually surprisingly useful here. How can standard deviation be useful in such a context? So think of how many dialects there are in these two languages. Let's say A and B. How many different dialects? What are dialects? Dialects means in Karnataka, people speak slightly different Kannada in Bangalore than in North Karnataka, in Dharwad, and slightly differently in Bangalore, and so on. So what happens is you have a language. Maybe you start with a single language, but slowly, because of geographical distance and so on, maybe not today in today's world, but in all earlier worlds before it was so connected, geographical distance means slight deviations happen in the language in different places, and these tend to sort of kind of spread out and become rather recognizably different dialects of language. Okay, and how will that is actually variation. Okay, the words undergo some standard deviation, and standard deviation increases with time. So in some sense, time can be measured using standard deviation. In other words, how many different dialects you have today is a measure of how long the language has been around. So if you say language A has many dialects and language B has fewer dialects, it's probably likely that language B came to that place more recently than language A came to its place because there are more dialects there. So that way, standard deviation can be a measure of time. So this happens in biology also. There are more varieties. So when I was giving this to some biologists, so they said, okay, we know some examples. There is much more variety of bacteria than there are mammals or something like that, because they have been around for much longer. There is much more variation among bacteria than among some later species. So that like that. So in time, in other words, what I'm saying here is in many situations, standard deviations occurs with times. And so it becomes a measure of time. When you cannot measure time directly, you can use standard deviation today to measure time before. Okay. So as I said, I may have lost some of you with some of the explanations here, but let new topic. So if I lost you, you can jump back again. Okay. So I come to sample service. Okay, what is sample service? Sample service is this incredible idea that you can ask something to a few thousand people and you can get a better insight into the state of the populations the size of India, let's say with millions of people, than if you try to ask everyone. Okay, it is a very paradoxical sounding idea. It works. And again, it's a surprisingly new thing. I mean, history is old, but sample surveys is like less than 100 years old. Okay, largely. Okay, maybe there were a few surveys before. See, I mean, suppose you want to know something. So this tells that instead of going to all the millions of people and asking everyone, you will get a better information by asking a few thousand people. Okay, how is that possible? Okay, so this doesn't seem believable, and people didn't believe it, by the way. So lot of resistance to this kind of ideas. The people dismiss them as newfangled ideas, blah, blah, blah. India luckily happened to be one of the few places in the developing world which has good statistics, and this happened due to people like PC Mahalanobis, who established ISI. He also started sample surveys in India. So I will show you an example how this happened. So this is an example from a jute survey in the West Bengal. Okay, so the problem was you want to forecast how much jute is produced in the next year. Okay, so what you can do is you can go to all the jute fields and then ask everyone. Look at what is happening and then make an estimate how much will come and how much is not coming, etc. And so on. So what happened was like this. The government did a survey. They were not willing to accept the sample service method that Mahalanobis was advocating. So what the government did was, this C means complete enumeration, means they went to every jute field, maybe in West Bengal, and they asked, they studied what may happen there, and they estimated how much will happen. Okay, so and PCM said, okay, I will do it my own way, and I will just do a sample survey. What was the difference? So the government, you had to go to every field, jute field in Bengal, then you need a lot of people, right? So 33,000 people were employed to do this survey. And it cost them 82 lakh rupees in that time, in 1940s. And they estimated that there is a unit called bale in which this jute is measured that is supposed to be 400 pounds. So they estimated that 6,304 bales are going to be produced, estimated output. PCM Mahalanobis was not planning to go to every place. So his sample survey needed fewer people, only 700 people. And of course, that means he spent less money also, 8 lakhs. And he came up with a different estimate, 7,540 bales. And when the next year, when they saw the actual output, it was 7,562 bales, which is obviously PCM's method was better. So how does that happen, that you go to every possible place and study, but you still cannot get the right answer? Whereas with a sample and with a small number of things, he could do that at 1/10 of the cost, you see. One of the points is the following, that, yeah, you don't really need. So there is some statistical regularity in the world, and you can exploit that. Second is that when you employ 33,000 people, you have no control. You cannot ensure that they are well trained. So with 700 people, you can give them good training and other things. So many factors kick in. But after that, he was able to convince the government, and sample surveys has been a strong point in India for a long time. Well, recent government has been suppressing a lot of data, which is actually quite dangerous, because this is one of the most important things a country should do, is to keep track of all the data. But if data is not kept properly, that can have long-term consequences. So anyway, this is some history I have written. So that led to this NSO, CSSO. NSO is National Sample Service Organization or something like that. Central Statistical or Central, I don't know what it is. Okay, I forgot. Oh no, it should be CSO and NSSO, I think. Okay, anyway, so there is a National Sample Service Organization, etc. Okay, so random sampling is the way to do the thing. So here is a nice question of sample sizes. Okay, so here is, okay, unfortunately, I think I didn't make a, I didn't make a poll for this either. Okay, it's unfortunate. I didn't notice. So a worldwide survey is, so all the time polls are conducted. So here is a question for which you can think about again. A worldwide survey is conducted to find out people's opinion on some topic, let's say. Maybe whether you believe climate change is happening or not. It could be something else. It could be, do you think Trump is an intelligent person? It could be something, whatever else of interest. Okay, the polling, let's say, organization chooses a random sample in each country. So they publish country by country data. There are these Gallup polls which do this, for example. So suppose they go to Pakistan and they do a sample of 1,000 people to get a yes/no question. Okay, so you believe in climate change? Yes, no. Okay, so 1,000 people were surveyed. So Pakistan has a population of 20 crores. So how many people should be surveyed in India? Okay, so how many people should be there in the sample? If in Pakistan you sampled 1,000 people, then how many people should be sampled in India, which has 140, about 7 times the population of Pakistan? Okay, actually this would have been ideal to make a poll out of here, right here, but I did not. So I'll give you 10 seconds to think about it. So what do you think? Should it be larger than 1000, smaller than 1000, or same? What should it be? Or if it's larger, how many times? Should it be 7 times larger, or should it be square root of 7 times larger, since I mentioned the square root law? Or maybe should it be square, 7 square times, 49 times? Okay, I hope people have thought about it. Answer is actually, it's exactly the same. Okay, you need only 1000 people, not 7 times square root 7 times 7 square times. No, the square root law is about the square root law that I mentioned is how many times you toss. In sample surveys, it is how many people you sample. It has nothing to do with the population size. Okay, the population size doesn't matter. If you are sampling 1000 people in Pakistan, to get the same accuracy in a sample in India, you should take 1000 people. People get completely surprised by this kind of stuff. I mean, so since we are talking about CMI, I mean, so your director, Rajiv Karandikar, he has conducted many polls. I mean, he has participated in many polls in election pre-polls and so on. And he has given talks on this also many times, and he emphasizes this point a lot. This is one of the very basic points of statistics, which is not well known even among mathematicians. Mathematicians also give wrong answers if you ask this question. Okay, so it turns out that the accuracy of your survey depends on the sample size, not on the population size. So it doesn't matter. Okay, so strictly speaking, accuracy goes down like the square root of the sample. Goes up like the square root of the sample size. So if you want to increase the accuracy by 2, you have to take 4000. But whether you do it in Pakistan or India, it's the same. Okay. Okay. So again, change of topics. So I deliberately chose a topic like this so that because I remember myself when I was a high school and college student, my attention span was not very great. So I thought that if there are distinct parts, maybe people will find it easier to follow. If you lose track in some of them, you can still follow in the others. Okay. Okay. So statistics and the mind. So by the way, it's by now clear that I'm not giving you a systematic introduction to statistics. That is for a statistics course. Here we are just taking a kind of bird's eye view or a survey of statistics. Okay. So let's say, okay, here is a poll coming up. Okay, be ready to push the buttons. Okay, here is a person about whom I'll tell you something. Okay, so there's a person X. It's either a doctor. I tell you that it's either a doctor or a mathematician. Okay, so one of the two. So here is you have to decide whether it's a doctor or a mathematician. I'll tell you a few things about the person, and then you have to make up your mind whether the person is a mathematician or a doctor. Okay, so what data do I give you? Okay, so I tell you that X is actually a man. He's intelligent, very systematic, extremely introverted, doesn't like talking to people, very absent-minded. Okay, so these are the things that I am telling you about X, who is either a doctor or a mathematician. Now you have to decide whether it's a doctor or a mathematician. Okay, so maybe run the poll.
Yes, sure, sir.
Okay, please make an intelligent guess based on what you think. Let us see.
Mathematician.
People don't have a good opinion of mathematicians. Yeah. Okay.
It's
So
from experience, like self-experience.
Okay, I see. Yeah, mathematicians are doing very badly. Okay, so come on, someone push for doctors. Okay, so
Nearly everyone has gone for mathematicians.
Okay, 59 and 7. So there are a few people who haven't voted. Okay, still people are voting. Let's give it another 10 seconds. Okay, I think it has stabilized.
Yeah.
So can everyone see? So it looks like, so now people can see, right? So 61 people think that it's a mathematician. Only 7 people think it's a doctor. Okay, thank the 7 people and then close this for a moment. Okay, so what is the answer actually? The answer is, so that is the question and you have already answered. So the correct answer is more likely to be a doctor. Okay, so those 7 people are right. Why? Let's admit all your stereotype of mathematicians. Okay, let's assume that mathematicians are more likely to be intelligent, systematic, introverted, absent-minded. Let's assume that these are more likely properties or qualities among mathematicians, let us say. Still, this person is likely to be a doctor. Why? See, how many mathematicians are there in the world and how many doctors are there? So did you think of that when you answered this poll? See, even let's say mathematicians are 10 times more likely to have these qualities than a doctor. Let's assume that, I mean, of course, it's not absolute, right? Doctors can also be absent-minded, etc. So let's say mathematicians are 10 times more likely to have these qualities than a doctor. But there are 100 times more doctors in the world than mathematicians. So what is this person likely to be? More likely to be a doctor, no? So this is one of the most common statistical fallacies in the world. In technical terms, it is probability A given B is not probability B given A. So what does this mean? What you are thinking is that if a person is mathematician, he is likely to have these properties. Therefore, if a person has these properties, he is likely to be a mathematician. That is false. That is an incorrect conclusion. Okay. So that is what I am saying. So I hope what I said was clear, that even if mathematicians are much more likely to have these qualities, there are many, many times more doctors than mathematicians. So the person is more likely to be a doctor than a mathematician. Okay. So there is a textbook example of the same.
Excuse me, sir.
Yes.
Yeah, I had a question.
Sure.
Regarding a previous slide, the slide about the sample space, like the 1000.
Okay. Oh, this one. Okay, sorry. This one.
Yeah. So you said the accuracy of the sample space depends upon the total population, right?
No. It doesn't.
As in on the sample, like the total population of the
sample size. It depends on the sample size.
Yeah, sample size, but it doesn't have any relation to the percentage that the sample size is of the total population.
No. Okay. So I glossed over that point. As long as the sample size is very small compared to the population size. Okay. Here, I mean, that is the realistic situation. We are never going to sample half of the people in a country. Okay. So sample survey is where you take a very, very tiny portion of the population, extremely tiny. So 1,000 people in a 20 out of 20 crores. What is it? It's not a fraction even. It's a very tiny number. So for those who understand this, the difference is when you do sample, if your population size is k, then beyond square root k samples, the sampling with replacement, without replacement starts mattering. They differ. But as long as you are below that, this is correct. So your question is valid, but always sample sizes are going to be very small compared to population size. As long as that relationship is not violated, it doesn't matter how large the population size is. Okay, so for example, if the sample size is 1,000 and your population size is, let us say, more than 1 million, then it doesn't matter whether it is 10 million or 100 million.
Okay.
It's the same. Okay. Okay, let's come back to mathematician doctor. So there is a textbook example which many of you may have seen, not high school students, but college and undergrad students may have seen. It is called Bayes paradox. Actually, what I gave is actually the same thing in a different guise. So this is actually important. It's a textbook example. So let me go over that. So there is a disease, a somewhat rare disease. So 1 in million people have the disease D. Okay, and there is a test. Like now everyone is familiar with the notion of test because of thanks to corona and so on. So what is a test? They take your blood and put it on some chemical or something, and if it turns red or blue or something happens, etc. Okay, so test is positive, means it's indicating that you may have the disease. Test is negative, means that it is indicating you don't have disease. Of course, no test is accurate, so this could all be wrong. So there is a test T to check for this disease, which is 99% accurate, let us say, which means that if you have the disease and you get tested, with 99% chance it will show positive, with 1% chance it will show negative. Or if you don't have disease and you get tested, with 99% chance it will say you don't have disease, with 1% chance it will say you have. Okay, so it can make mistake on 1% of cases. Now, one of your friends gets tested, is found positive. He is very depressed. He or she is very depressed. So how do you console the person? Okay, first you say, oh, no, these tests are not accurate, don't worry. Then the person checks, you can check everything on internet and says, no, the test is 99% accurate. So it means that the person is 99%, has 99% chance to have the disease, right? Is that right or not? If you say it is right, you are making the same mistake. Probability A given B and probability B given A, they are not the same thing. So what is the chance actually that he or she has the disease? So this is a disease which affects 1 in a million people. It's tested by a test T, which is 99% accurate. So person is tested and found positive. What is the chance that the person actually has the disease? It's actually 0.0001, not 99%. It is 0.0001. Why? Okay, one thing you should notice is that although it is a very tiny number, so your friend doesn't have to really get depressed yet, but it is a tiny number, but it is way larger than the 1 in a million that was a priori the chance. Okay, a priori it was 1 in a million, it's way larger than that, but still you can perhaps take some consolation in it. Mathematically what is behind it is called Bayes rule. If you do Bayes rule, you will find this. If you don't know what it is, don't worry about it. I will show you in picture what this is. Unfortunately, I don't know if this picture is very clear. There are in this picture, this is a picture each dot is supposed to be a person in a population. Okay. Most dots are brown, some are blue, some are red. Okay. I will explain what they are. These brown dots are healthy people. Okay. Healthy people who test negative. Red dots are healthy people who test positive. And blue are diseased people. Okay, so let's assume that our test is so accurate that it will catch every diseased person. So I'll make the test even more accurate. What it does is if someone has a disease, it will catch for sure. But if someone doesn't have a disease, it will with 1% chance say that they have disease. Okay, so that is the situation illustrated here. So everyone is a person here. This is our entire population. The brown ones are those healthy people. If you administer the test to everyone, imagine that you administer the test to everyone. What happens? All these brown people were tested negative. All the healthy people, 99% of them tested negative. That's all the brown people. The red ones are healthy people who tested positive. That's only 1% of the people who don't have disease. And blue are diseased people. They all tested positive also. But what you see is that, most people are healthy, right? So 1% of them test positive. So if you look at all those who tested positive, red and blue, even then, the number of people who, the fraction of red is actually much larger than the fraction of blue among the red and blue, right? Because what fraction is red? About 1% of the entire population is red. What percent is blue? Only 1 in a million is blue. So that's actually the point. So if you know person tested positive, it's more likely because the person is healthy and got tested wrongly. Okay, so that's actually the same as this. I leave it for you to make the isomorphism. So how is that related to this doctor mathematician question? So you equate mathematician with diseased and doctor with healthy or something, then you will get the answer. Okay, so it's actually the same. So here, okay, I had another picture. So if I look at only the tested people, tested positive people, this is what I see. You see a large fraction of red actually. That means they were the wrongly tested ones. That's what it is. Okay. So one more thing about the psychology of probability. So this is actually, so some of you, I don't know if you people read popular physics, math, science books. So there are these people, Kahneman and Tversky, they are economists, but they have worked a lot on psychology of probability. Okay. So that example of mathematician doctor I gave is also from one of their ones, I think. Or maybe not, I now don't remember, but it's they call it representation paradox, but it just means Bayes paradox, that's all. So they found, they did a lot of things about the psychology, because their problem was the economics works with certain assumptions about rational decision making people and so on, which they believed was not satisfied in real life. So they did many things to show that people don't think rationally. So that here is an example of a very extreme example called the Linda problem. So the question that they gave is like this. So the Linda is a 31-year-old, single, outspoken and very bright. She majored in philosophy. As a student, she was deeply concerned with the issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. So you have to choose among the two options. Option 1 is Linda is a bank teller. Option 2 is Linda is a bank teller and active in the feminist movement. Okay, you can run the poll quickly. Again, we'll finish it in 30 seconds. So people can choose one of the two options. I have never seen this poll result myself, so let people do it.
Sir,
Okay, it's stabilized on 45 and 17. Okay, so the poll has stopped, right? So you can see the results of the poll. Okay, I don't know what this thing is. So 45 people voted for option 1, which is Linda is a bank teller, and option 2 is some 18 people voted for that. Okay. Okay, what is the point here? See, what was the question? The question is choose the more likely option. First one is Linda is a bank teller, and second one is a more specific one. So this is a subset of that. Obviously, the first one is more likely. If A is larger than A contains B, probability of A cannot be smaller than probability of B, right? So the more likely option is definitely the first one. But it is somehow, it's not that people who are choosing the other one are foolish, or that is not the point. The psychology of probability is somehow a bit strange. So I don't know how to interpret these experiments, but a lot of people choose the second option. This is seen in many, many experiments conducted by Kahneman and Tversky, although it's a subset of the first one. Okay, so this, why that is, okay, I will leave you to think about. Overall, the human mind doesn't appear to have a natural ability to gauge probabilities. We have to train ourselves. Okay, so let me come. Okay, by the way, I'm close to 3:30. Should I stop right now? I mean,
So I think you can easily go for 15 minutes.
Are you sure? Is that okay?
Yeah, sure.
Okay. Okay. So then there are a couple of more things. Maybe I'll skip some, but I will tell some. Okay. So let me tell, for going further on this. Okay, this is also related to that. So sampling and selection bias. Okay. So quite often the psychology of works like this. So you can ask. Let me ask you the following questions. You can't answer it, but answer it in your own mind. So do you sometimes find that the bus you are waiting is the one that is most delayed? Or the queue that you are standing in will be the longest one, or that the traffic jam you are in is the one that takes longest to clear, whereas you are in a traffic jam so often, but the other side, the opposite side vehicles are moving freely. Why? I mean, why did nature select you to do all these bad things to you, right? So probably many of you would have felt this at various times. Why do these things happen? Is it just that is it illusory, or is it true that these are happening to you? Well, it's not entirely illusory. There could be a psychological aspect to it, but this one is not a psychological aspect. This is probably true. Answer is because you're a typical person. See, why are you in a longer queue than in a shorter queue? What is the difference between a longer queue and shorter queue? Well, the longer queue is the one with more people. The shorter queue is the one with less people. So where are you more likely to be, among more people or among less people? Among more people. So you're more likely to be in the longer queue. Okay, it's similar to the one that we had before. I mean, with okay, or for that matter, traffic jam. Traffic jam is a place where there are lots of people stuck. So are you likely to be among a lot of people or among a fewer people? So you're likely to be among a lot of people. So that is why you do have these situations. Okay. So this has nothing to do. I mean, this has nothing to do with the title written here, sampling or selection bias. But this is something that one has to realize that many a times this is because this is what you should expect to happen. Okay, so now let me tell you something else, which is a funny story about, this is a story from the World War II. So this is a true story actually. So it was a problem of fixing airplanes in World War II. So you see, in World War II, when US and UK and so on were fighting against Germany, okay, wartime is usually a time when shortages are heavy. So you cannot waste metal or precious things. You usually try to conserve them. So they had this problem in the United States that, okay, planes get damaged all the time. Fighter planes get damaged and all that. So they have to fix these things. But you can't just use metal and all that resources too much. I mean, you have to prioritize your options, and you have to sometimes let go. You cannot fix everything. It's not like, okay, if the pilot seat doesn't have cushion, probably you'll have to ask him to go as it is. So you can't fix all the problems. You have to fix some, you have to prioritize. So how to prioritize which ones to fix? So in particular, there was this problem of planes having damage due to bullets. So some engineers made this to see how to prioritize. So they saw this, so they measured. You have to measure, you have to know the data to do anything. They checked the planes, how much damage there is to different parts of the plane, so that they can prioritize which parts to fix and which parts to not fix. So here is the part of the plane, engine. So bullet holes per square feet among engines is 1.11. In fuel system, some 1.55 more than in the engine. That means there were more bullet holes in this part of the plane. Fuselage is the part where you sit in a plane, the cylindrical body of the plane. There was much more damage, 1.73 per square foot. Okay, by the way, not because it's big, it is per square foot, it is big, more. And some rest of the plane, maybe wings and tail or whatever, it is 1.8. So what should one do? So you have to prioritize. So the engineer said, okay, so this is getting more damage, so we should prioritize. So prioritize these other parts, wing and tail, then fuselage, then fuel system, and then if left over, you do for the engine. So they went to a statistician, a very famous statistician, Abraham Wald. Wald said, very good, only reverse the priority. First fix the engines, then fix the fuel system, then fix the fuselage, then the others. Why did he say that? This is one of the things that statisticians are alert to. Statisticians are always alert to the point that the data that you see is already selected for you either by your sampling biases or by nature itself. In this case, what Wald was imagining, which the engineers didn't think of, is, okay, why is there less damage in the engines? Okay, why are fewer planes having engine damage? Well, he realized probably because damage to the engine is so serious that they don't come back if they get damaged. Whereas this fuselage part is such that if it's damaged, it doesn't matter. Planes at least can come back. So unless you imagine that there are missing planes which have been shot down, you will not realize that the data may be actually the opposite. What is the more serious damage is to the engines, and the less serious damage is to these other parts. So you see how a statistical way of thinking can make a crucial difference to decision making. It's a very nice example of actual use. How many planes have been saved because of this? One can only imagine. So, okay, so that is one example of a selection bias. What I mean by selection bias is, here the planes that you have data on are the planes that came back. You don't have data on the planes that didn't come back. That's the selection bias. Your sample is biased. So many times people tell you at home, oh, these youngsters, these days people are not healthy. My grandmother used to lived for 75 years. She is so healthy, etc. Probably all of you have experienced this kind of stuff. They'll tell about their grandmother, grandfather who lived, and at 70 she could eat groundnuts or whatever else. But these days people are having problems at 50 and so on. So Is that really correct? I mean, is it really true that people were healthy in the past, or is it wrong sample? Okay, so there is a very simple way to find out. I didn't make a poll for this, but I don't need the results. I can tell you what the poll is. So I want to find out how many people die under the age of 10. Okay. So how would you do that? You take a random sample today and survey that. Okay, how many people died under 10? Let's say you see the people born in the year 2000 and then see how many of them died. But if you do sampling in the wrong way, do a wrong sample, namely take the sample of all our grandmothers, let us say. Okay, so let us say our sample for an older period. I want to know what happened to people in the 1950s. How many people used to die under the age of 10? So let us use our sample of grandmothers to estimate that data. Okay, so the poll, if anything, you raise your hand sitting in your home if one of your grandmothers died under the age of 10. Okay, so I will give you 10 seconds to raise your hand. Okay, I will expect that none of you raised your hand because nobody's grandmother died before the age of 10. Can we conclude based on that nobody used to die under the age of 10 and those times? Of course not. The point is the set of grandmothers is a very bad sample of the population of that time. They are very special because they became grandmothers. Okay, so that's not a random sample. You have to use a random sample to get information about a population. If you sample your friends and take their opinions, you don't get the true opinion of the population. This is why people get surprised about election results or something else. None of my friends were voting for these people. How did they get selected? Well, your friends are people like you. That is what you have been trying to get friends. I mean, your friends by definition are people like you. That's not a random sample. Okay. Okay. So there is strength of evidence. I don't know whether I want to go over this. Maybe I skip this section. So yeah, okay, maybe I skip this section. Let me just do this section, the importance of small probabilities. So sometimes small probabilities are important. You might think that small probabilities are not important, but they can be. For example, I said earlier that that 99% are within 3 sigma, and then I said that in CMI, maybe they care only about the people who are beyond that. Okay, so like that, many times small probabilities are important. So what, for example, when? Okay, uh, if it's small probability, 1 in 1,000, why should I care about it? It's not likely to happen. Well, it depends on what it is. So suppose that if it's well, it depends on what it is, right? Okay. So suppose the chance of getting hit when crossing the road across your home is 1 in 1,000. That is very dangerous because you will cross it thousands of times. So you are going to get hit. So 1 in 1,000 is not small enough for that purpose. It may be small for some other things. But so in other words, when there are a large number of trials, a small probability could be important, right? A large number of attempts or trials, then a small probability could also become important. So there is this whole subject. I'm just telling you a little bit about some deeper aspects of probability and statistics. This is called large deviations theory, which is the study of very tiny probabilities. Okay. So more precisely, it makes estimates of such small probabilities. People wonder why we care about such small probabilities. And they also worry not only what the probabilities are and how they occur when they do. Okay, let me give you some examples. So I'll come back to this example. So let's take this example. So what is illustrated here is an example of this large deviation theory. By the way, large deviation theory is also nice. I mean, so one of the leading figures in that is a very famous Indian mathematician or Indian origin mathematician, Varadhan, who developed a large part of large deviations theory. But the basic, I mean, it's a technical subfield of probability. However, the very basic point of it is actually quite something that everyone can understand. And I want to try to explain something here a little bit. Okay, what I have done here, this is an experiment that I ran on my computer. Okay, so you imagine that there are insects which are being born at the origin. Okay, so an insect is born and it wanders and it dies. Okay, so I give every insect has a lifetime, which is I give unit lifetime, and it wanders without it is blind. Think of it as blind. So it wanders without any direction and it just dies. Okay, most of them are like this. So what is this one? This is the first one which reached a distance of 1 kilometer from its starting point, or for 4 kilometers from its starting point. Okay, so this one you think of as 1 kilometer. This is the first insect which reached 4 kilometers from where it was born. I did this many times. Most of them were like this. After thousands of trials, I got one which reached, every time I checked whether that went at least 4 kilometers from its starting point. And the first one that got selected was this. Okay, so is the experiment clear? It is strange. What is remarkable about this one is that if you look at this fellow who reached the 4 kilometers first time, first insect that reached 4 kilometers, you see it more or less traveled straight from its starting point to end point. Was it an intelligent insect by any chance? Somehow, and so as I ran the computer simulation, there was an intelligent insect born which traveled like that, straight to where it wanted to go. It didn't waste any time wandering around. It went almost straight to its destination. How did that happen? Of course not. It's a computer simulation, so there is no purpose. But this is the point of large deviations theory, that the insect that went appears straight and it gives the illusion of purpose and design. But that's not the case. Actually, what happens is the following. The moral is the following. When an unlikely event happens, it happens in the least unlikely way. Okay. What do I mean by that? Let's explain here. Suppose there are two. Okay. Let me give another example. So what is an unlikely event? So always, I have read lots of popular physics books. Whenever they want to explain probability, usually they give a typewriter to monkeys to type. So, and usually they ask whether it will type Hamlet. Okay. So for some reason, monkeys have affinity to Hamlet. So the statement is that if you give a typewriter to a monkey, it will ultimately type the Hamlet, Shakespeare's famous play. Okay, so let's do a slightly different thing. We take some desi monkeys, so millions of them, we give them typewriters. So they are supposed to type until either they type the Ramayana or Mahabharata, let's say. Okay, let's say either of this will declare a success. If by mistake they type some Abhignana Shakuntalam or something, you reject. We are very demanding about our monkeys. They don't have to, they shouldn't miss a comma or anything. Okay, so what happens? So the claim is that the first monkey to succeed, okay, ultimately you keep running this experiment millions of years with millions and billions of monkeys. I claim that the first monkey to succeed will succeed by typing Ramayana, not by typing Mahabharata. Okay, and not only the first one, the first 100 million trillion monkeys who succeed. I'm talking about the successful monkeys. They will all succeed by typing Ramayana and not Mahabharata. Why is that? Simply because, why? Because Ramayana has more relatable characters to monkeys, or is that some other reason? Well, the simple reason is that Ramayana is about 4 times at least shorter than the Mahabharata. That's enough. And so the chance of on a single shot typing Mahabharata or Ramayana is extremely unlikely. Let us for simplicity say the chance of typing Ramayana is 10 to the minus 20. It is way smaller than that, but let's say it is 10 to the minus 20. And the chance of typing Mahabharata is way smaller because it is longer. You have to press all the right keys. So it is 10 to the minus 30. Both are unlikely. But if one of them happened, what is the chance that it was the first one? It is 10 to the minus 20 divided by 10 to the minus 20 plus 10 to the minus 30, which is extremely close to 1. So this is the statement that when two unlikely things happen, when one of two unlikely things happen, the less unlikely thing will is more likely to have happened. So that's what happens here. And this gives an illusion of design. For example, you can think of, for example, this is somewhat relevant to evolution. So you look at today, we are the only people with, only animals with a brain. We look at the evolution of the brain backwards. It seems like always it went on increasing in size. Okay, I don't know much biology. I'm making a cartoonish example. So if I'm wrong, excuse me. But I'm thinking that if you look back on the our backward trajectory, our ancestors, their ancestors, and so on, it looks like the brain size was always going on increasing till we reached this pinnacle. So was that the intention? Actually, no. The forward, when you look at the forward path of evolution, it is like a random walk, like these insects. But when you take somebody who succeeded like us and look at their backward path, that looks like a straight line. It gives you the illusion that it was actually headed towards this. Okay, so this is one of the insights coming from large deviations theory. There is another way in which very small probabilities matter. So I'll just end with this. This is the last one. I have 1 minute. I will end this. So
Sir,
this is just a, sorry.
Sir, least unlikely way means the one with less probability.
No, least unlikely one is the higher probability. So in this 10 to the
Within
minus
the
20,
two unlikely.
less unlikely. This is less, both are unlikely, but this is less unlikely.
Okay. So P will occur.
The larger P, the two P and Q are of completely different orders of magnitude. P is way larger than Q. Although both are unlikely, when one of them happens, it is more likely this event with probability P that happens.
Okay, sir.
Okay. So here is another weirdness of geometry in high dimensions, which is related to probability, and it underlines a lot of modern statistics. Okay. So one can explain it in a picturesque way. So imagine I give you a paint and a paintbrush. Paintbrush has a width of 5 centimeters. So your job is to paint the equator, because during my high school and so on, I used to think, not high school, maybe primary school, on all maps there used to be equator. It was a long time later I came to know there is no such line actually on the earth. So I would be more happy, maybe I'll give you a paintbrush and you are supposed to paint the equator. Okay, so what portion of the earth is covered by paint after you do this? It's a width of 5 centimeters and you draw around the circumference, right? So you would say it's very, very tiny. It's 0.0000. I calculated this. It's a very tiny strip around the equator that you have painted, right? Okay, so let's do the same experiment in a high dimensional sphere. Okay, what is this? Let's take a sphere in 10 to the 20 dimensions. Okay, if you don't know what is higher dimension, which is perhaps the case for many high school students, sorry, I cannot explain it now, but you imagine a very high dimensional sphere and you can do the same experiment. Okay, so again, a unit radius sphere in high dimensions in 10 to the 20 dimensions. And I again give you a brush of width 5 centimeters. The diameter is again 2 centimeters of the sphere. Okay, so 5 centimeters is small. The diameter is same as Earth. Sorry, diameter is not 2 centimeters. The diameter is the same as that of Earth. But the width of the brush is again 5 centimeters, and I ask you to paint the equator on this sphere. What portion of the surface is covered by paint? Okay, it turns out the answer is 99.999999%. So most of the area is actually covered, although it is such a huge one. So this is actually what is called the curse of high dimensions. And this is a fact actually. You can, if you know what this is, you can do a simple calculation, you will find this. This is a very big thing in probability called concentration of measure. So, but why would you care to paint in 10 to the 20 dimensions? Okay, so let me just explain that. Why would anybody want to paint a ball in 10 to the 20 dimensional space? Well, what is 10 to the 20 dimensional space? Think of a box of gas, okay, as you do in statistical physics. So you write the velocity components of the molecules. Usually there are 1 mole will contain some 10 to the 23 molecules. So each of them has 3 velocity components. So there are 6 times this many dimensions. So in other words, this velocity vector is a vector in 6n dimensions. So we do actually encounter high dimensional spheres. If you move if it's a fixed energy, if the kinetic energy, if you don't allow temperature to enter outside, inside or outside, this vector will lie on a sphere in that dimensional sphere. Okay, so that is what happens, and modern statistics deals with huge data sets, high dimensional statistics, whether geographical regions, DNA data, whatever else. So they're all those, the modern statistics has to deal with the problems of high dimensionals, which is the strange phenomenon that I have illustrated here. Okay. So that is what I want to say. So statistical problems in high dimensions have to deal with weirdness of geometry like this. Okay, that's enough. Sorry, I went.
In the case,
yeah.
In the case of the high dimensional sphere, for the normal 3-dimensional sphere, we are getting the ratio of area as the probability. But for the high dimensional sphere, what is the ratio that is we are taking as probability?
So
I
what is
mean, what
the
is
whatever
area in
is
high
the,
dimension?
whatever is the surface area painted? So what is equator is a great circle, right? Equator is a curve on the sphere. So we paint.
Yes, but in higher dimension, do we have the concept of area, or in
Yeah,
in two dimension we have
area.
perimeter?
Yeah. Yes. Surface area on the measured on the area of the sphere, on the surface of the sphere is meaningful completely. So it is how much area out of the total area is painted.
Oh,
Yeah.
in the n dimension we have any that surface area concept?
Yes. Well, you can call it surface area or volume, whatever you want to call it. There is a notion of surface area. Yes.
Okay, sir.
Yes. Yeah. I mean, so it is actually, strictly speaking, n-1 dimensional. I mean, what you call three-dimensional sphere, mathematicians usually refer to it as two-dimensional because the surface is two-dimensional. So that's why we use the word area. Actually, this is an n-1 dimensional surface if n is the dimension though, of the space, underlying space. So, but there is a notion of area. Yes. Okay. Okay. So that was all I wanted to say. Yeah. Thank you. And if there are any questions, I'll be happy to take.
Thank you, sir. It was really a wonderful talk. How you like showed us many paradoxes, starting from Simpson paradox, and then the World War airplane, and like Doctor mathematician. That was all. It was really cool, and I hope everyone has enjoyed it. And now we are open for questions. So if people have any question, then they can unmute themselves and ask directly to the professor.
Excuse me, sir. I have a
Yeah.
question.
Yeah.
As you said, it is at times better to take a small sample of, say, 1,000 people, and it gives us a good opinion, a good estimate of what is happening.
Yes.
Why don't we just take a sample of 1,000 people out of the whole country and ask them to vote in elections? That would be much easier.
Yes, I mean, so, but yes, that is true. Actually, it is true. I mean, so, but people will be unhappy for sure. Okay, so, but this is correct. If you want to, for example, if you want to check, suppose this question of EVMs are there, right? Whether EVMs are actually counting correctly and so on. In such a situation, if you want to check, now, not every kind of fraud can be checked by statistics, by the way. So if you just want to check whether EVMs are counting correctly, then a sample is sufficient to get say with reasonable confidence that it is or it is not. A very small sample can be. Okay. So it is true that a very small sample of people you can get the same opinion as the full population. It is actually true, but real life is complicated and people have various things. So you cannot just replace an election with this. Right. I mean, people will be unhappy. And of course, as I said, all frauds cannot be detected by statistics. So for example, EVM, there are different kinds of frauds, but if suppose we are talking about malfunctioning EVM, sometimes EVMs can malfunction. So you have the paper trail and the EVM and you can tally that. But you don't have to do it for all the votes. You can do it in out of some, this is something again, a study that was done by Cavendish and his co-authors last election. So they did, for this kind of fraud, how many voting machines should you check? And you don't need like, I mean, so the number of voting machines that were used are, I think, in the order of, now I forget, it is like lakhs or million or what, I mean, I forget now actually. But the number that needed to be checked was only like 500,000, that's all. For this kind of statistical accuracy, it cannot guard you against the fraud where some goons are coming and stealing your EVM. Okay, that cannot be detected by statistics. That is different.
Thank you, sir.
Okay.
Excuse me, sir.
Yes.
On one of the slides, it was written that standard deviation of a binomial n comma p is the formula was there. So, in what context are you referring to the binomial here? Means what is exactly the binomial?
Okay, let me go back. Maybe this one. Here,
Yeah.
because the sample. Okay, so it is a yes/no question. Let's say. Okay, so we are asking a yes/no question. What percentage of people believe in climate change? That's what we want to know. in the actual, in India, maybe there is an unknown percentage of people who don't believe in climate change, let us say. Maybe 30% don't believe. We don't know that. That's what we are trying to estimate. Okay, so P is that underlying proportion of people who don't believe, let's say, in climate change. But N is the sample that we are picking. N is the how many samples we are picking. In our sample, how many of them will say, I don't believe in climate change? That will be a binomial random variable with this distribution.
All right.
Okay?
Sir.
And okay, this is not exactly correct. I should divide this by N to get this standard deviation. What I will measure is, this is the number of people in my sample who say they don't believe in climate change. So I'm going to divide it by N to see what proportion in the sample say they don't believe in climate change. That proportion is what I estimate to be the population proportion. The claim is the accuracy of this estimate is given by this. You can ignore the numerator, it is 1 by square root n. So if you want to double the accuracy, you have to increase n by 4 times. That's the statement.
Okay, sir. Thanks.
Okay. Okay. Any other questions?
If there are no more questions currently, then maybe you can mail us afterwards and we can take up with the professor. So,
yeah, sure.
So I think, yeah, now we can come to conclusion. So thank you, Professor, once again. That was really, really wonderful talk. And people
Sorry,
are
sir,
also
I
asking.
have a question.
Oh, okay, yeah, sure.
I
go
have a
ahead.
question.
Yeah, sure. Go ahead.
Last one.
Sure.
So, sir, the lesser sampling works just because we can control the data more easily.
No, the lesser. Okay, so lesser sample. Okay, first of all, small sample is enough to get a picture of the whole population. This was the first question also. Like, why don't we just ask 1,000 people to vote? Yeah, it is true that one can get the correct, get probably the same results from the whole population as from a small sample. That is true. But second is, in conducting of the sample survey, it will help because you have to do less work, so you can do it well and with less cost. So for example, if you are trying to send 33,000 people, imagine the complexity of the job of sending 33,000 people, training them to collect data, and they have to actually do it and not write the data themselves and come back, for example. All this you have to know. How will you know? Right? So that is very difficult. Whereas with 700 people, you can train them well. That matters a lot too. Okay, but statistically, the point is the accuracy is already with a small sample, you get the full accuracy. If you provided, you choose the sample at random. Okay, maybe did you have a further question? I kind of interrupted you when you just were asking.
Sir, I have a question.
Is that okay?
No, thank you, sir. So, yeah, just the practical implications of the statistics kind of get in the way.
That also, yeah. So the human aspect of it also gets in the way, indeed. Yeah, there are two things. One is the first statistical aspect, which is that small sample is enough in principle to get the accuracy. Second is that human things make the complete enumeration a complete pig's breakfast out of. So that's the problem.
Yeah, thank you, sir.
Sure.
Thank you. Wonderful.
Sir, I have a question.
Yeah.
Sir, the sampling which we are doing, does it have a specific method? I mean, we just select at random any 1,000 people out of.
Right. That is very important. You select at random. That is the point. Random is, okay, here I said select at random means every subset of 1,000 people should be equally likely. That is what it means. Okay.
All right. So we can select anyone and everybody.
So, but not any 1,000 people. I mean, you have to choose them at random. That is the claim.
Yeah,
for example,
random, yes. Okay.
It is not a good idea to stand outside a 5-star restaurant hotel and then ask people who come out. Okay, that's because that population is automatically biased towards a certain kind of population.
All right.
Okay.
It's 4 o'clock.
Means.
Huh?
How will we select the sample?
Okay, for that, okay, that is actually an issue. So many times people have to kind of resort to simpler methods because completely at random, firstly, you have to have maybe a list. Okay, one option is imagine that you actually have a list of all the people, then 1 million people, then you can just pick on a computer, you can pick 1,000 random out of 1 million, and then you can go to those people with those serial numbers. In principle, that is what you are supposed to do, but in practice, that is exceedingly painful. Okay, so that's not the way it is done. People resort to various approximations such as systematic sampling, etc. Systematic sampling is maybe you take a telephone directory. Nowadays, there are no telephone directories, but let's say you take a telephone directory and choose every 1,000 person starting from the beginning. It's a bit easier to do that and then call them up. Okay, that's not exactly a random sample, but it sometimes works. If you believe that, this will not bias your sample in any way.
All right, and the outcome we are expecting means the parameter we want to measure.
Yes.
Is mathematical proof that random sampling is a better method?
Well, I mean, no, I mean, there are actually sometimes there are other methods which can be even better than random sampling.
No, how do we exactly prove? I mean, is there any mathematical theory behind it?
Mathematical theory is exactly this. You can take the standard deviation as the statement. Where did I write that? I mean, there's accuracy which I wrote there. Where did I write? This one. You can take this as your, so what this is telling you is that based on a sample, if the actual probability is P underlying, which let's ignore, it is somewhere between 0.2 and 0.8, let us say. We don't know what it is. Let's say it is between 20% and 80%. Some underlying population, which proportion of people of a particular category in a certain population is between P 20% and let's ignore this. What this is telling is your estimate is with high probability within 1 by square root n of the actual P. That's what it is telling you, where n is the sample size. So depending on how much accuracy you want to measure within 2 decimal places, then your 1 by square root n should be less than 0.01. So n has to be correspondingly big.
All right, sir.
So that is how you say it.
All right.
Okay.
Yes, sir.
Thank you. And we also have Professor B.V. Rao with us today in the audience. So, Professor B.V. Rao.
Yeah, hello, B.V.
How are you?
Yeah, good. So,
excellent.
Huh?
Excellent lecture.
Thank you.
That's
well,
good.
they have heard all this from you already, but these are high school students, so okay, I thought.
Excellent.
So thank you once again, and I would like to thank all the participants. So our next lecture will be at 5:30 by Professor Alok Ladha of CMI. He will give a talk on from gold to gluons of the story of quantum mechanics. So please do join us. And then the last talk of today of the qualifier camp will be at night 10 o'clock by Professor Ravi Vakil of Stanford University. His talk is named as From Doodling to Mathematics. Hope to see you all there. Thank you. And thank you, Professor Manjunath, once again.
Thank you.
Thank you, Professor Manjunath.
Thanks. Okay. Yeah, it was a